Hi, grade 12s, welcome. It's Saturday Extra and it's time for Physical Sciences. My name is Tinyiko Kosa and today's lesson is lesson number 21. We're going to talk about optical phenomena. So let's just unpack it. Optical phenomena. This lesson will focus on light and matter. We'll be talking about photons of light. Think you're not hearing these for the first time. We did this when we were talking about photoelectric effect, so it's something you should be familiar with at this point in time. We will be talking about emission spectra. We'll be talking about absorption spectrum. We will talk a bit about the red and blue shifts, and lastly, we'll be talking about scattering. Okay. Now, let's talk about light and matter. Remember that when we did photoelectric effect, we spoke about light having a dual nature. One, it could be looked at as something that has a wave nature, and it can also be looked at as something that has a particle nature. So when we talk light and matter, those things should come into such discussions. Now, when we have light falling on matter, a number of things can happen. This light can be reflected, so reflection can take place. Sometimes the light is absorbed into the material. Sometimes this light is allowed to pass through, so the light is transmitted. It goes through the object. And sometimes the light is emitted by the object. In other words, the object gives back that light. And lastly, when we talk light on matter, this can also happen. Photoelectric effect can happen. Now, remember what photoelectric effect is? You shine light on metals. This normally happens with metals. Light on metals. And when you do that, electrons get ejected from the metal surface, okay? And that is called photoelectric effect. In other words, these electrons gain some energy, get excited, and they actually come out of the surface of the metal. Right, so this is what basically happens when light is shined or is shown on matter. When we look at light as having a particle nature, we can't talk about light having a particle nature without touching on photons, because these are the particles of light that we say are forming this light. And what we also know about them is that these photons of light are actually carrying energy. All right. This energy of light, the photons, are packages of energy in electromagnetic radiation, and the energy they carry is said to be quantized. In other words, this energy is discrete. For that particular photon, the energy will be that particular amount of energy. It can't be more, it can't be less, it has to carry that amount of energy. So we say the energy is quantized. For a photon of green light, for example, that photon will carry that specific amount of energy. It can't carry more, it can't carry less. It will have that amount of energy. That's what we mean by the energy being quantized. All right, and this energy is defined according to Planck's equation, energy equals HF. So we can use this equation to actually find the magnitude or the size of the energy we're talking about. Okay. Let's look at one example to try and revise some of the things we've done already in terms of energy carried by photons. A beam of light has 2 electron volts of energy. Find the frequency of the light, and then B, find the wavelength of the light. Down here, we're given a few more, some information. We have to use that to find the frequency because we have the energy. But we need to know that the speed of light in a vacuum is 3 by 10 to the power 8 meters per second. H is Planck's constant, 6.63 by 10 to minus 34. And we also need to know how to convert from electron volts into joules of energy. 1 electron volt is 1.6 by 10 to the power minus 19 joules. Okay. Now let's try to answer the number A. Number A, we are to find the frequency of the light if the energy is 2 electron volts. Number A. Let's start by converting 2 electron volts into energy in joules. 1 electron volt carries an energy of 1.6 by 10 to the power minus 19 joules. So 2 of them will carry that. And what is that? We can work it out making use of a calculator where you have got 1.6 by 10 to the power minus 19 times 2. So it's 2 times 1.6 by 10 to the power minus 19. And what's your answer there? The answer is 3.2 by 10 to the power minus 19. So the energy here is 3.2 by 10 to the power minus 19 joules. We have to work in joules. That's why we are converting from electron volts into joules. The energy that is carried by this photon is given by HF, E equals HF. So it will mean that 3.2 by 10 to the power minus 19 joules of energy would be equal to Planck's constant 6.63 by 10 to the power minus 34 joules per second times frequency. So we are to find the frequency, so we will substitute the other values for energy and for the Planck's constant. Therefore, our frequency F will be equal to 3.2 by 10 to the power minus 19 divided by 6.63 by 10 to the power minus 34. Okay, so that's what we have. And we can quickly get the solution to that. Would say this is 3.2 by 10 to the power minus 19 divided by 6.63 by 10 to the power minus 34. And what do we get as the answer? The answer is 4.83 by 10 to the power 14. So it is 4.83 by 10 to the power 14 hertz. Okay? To the power 14 hertz. That is the frequency of this beam of light. Okay? So that's how we use Planck's equation to solve these kind of problems. Remember, it had a second part to it. It said also find the wavelength of this light. Number B. Now, how do we find for the wavelength lambda? Okay? We can use the wave equation C equals F lambda. Okay? Because we know the value of C is a given, it's a constant. So we can say, all right, this is 3.0 by 10 to the power 8. That is the speed of light in a vacuum equals, we now have the frequency, so we can calculate for lambda. The frequency is 4.83 by 10 to the power 14 hertz times lambda. Okay? So we can say here that lambda is therefore equal to 3.0 by 10 to the power 8 divided by 4.83 by 10 to the power 14. Now, what is that? Can quickly calculate for that. This is now 3.0 by 10 to the power 8 divided by 4.83 by 10 to the power 14. What's the answer? What we have is 6.21 by 10 to the power minus 7. 6.21 by 10 to the power minus 7 meters, because we're looking for wavelength, lambda. Now, 6.21 by 10 to minus 7 meters is the same as 621 nanometers. Okay, now this is a very, very small distance. That is the wavelength of the light that brought that particular amount of energy, 2 electron volts. Right, let's look at example 2. Explain why different substances burn with different color flames. Okay, now I think practically we might have noticed this, that when you burn a piece of paper, for example, it has a different color flame to something that you may burn, being a rubber molecule or plastic molecule, things like that. So why are we having these different colors of flame when we burn different substances or different materials? Okay, now let's see how we try to answer this question. Now, we need to understand that when you burn something, you are supplying energy. Okay? When you burn something, you are supplying energy. So it's energy supply. That energy is absorbed by electrons in that particular material. Then when electrons absorb this energy, they get excited. So they gain this energy and they get excited. What we mean by electrons getting excited in science, we mean that these electrons move from the ground state to an excited state. What is a ground state? A ground state is a position of an electron in terms of energy levels. An energy level is depicted by small letter n. So energy level 1 would mean the energy level where electrons are occupying that first energy level. Would have n equal 2, n equal 3, n equal 4, and so forth and so on. Okay? Now, if, for example, this is where, in this energy level, this is where this electron, the green part, that's where it should be. That becomes the ground state for that electron, because that is the lowest energy level it can occupy. So that is the ground state for the electron. But when this electron gains energy through heating, it goes up, it gains energy and goes up to a higher energy state. Say this was n equals 2, then it goes to n equals 3 there. At that state, we say this is now the excited state. Excited state. This electron has gained energy. It is now at an excited state. So the excited state is not stable. In other words, this electron cannot spend much of its time up there. Any time when it is possible for it to lose that energy to go back to the ground state, it will do so. So this state here is said to be unstable. All right. Now, at that unstable, excited state, the electron can re-emit, can give off the energy it gained. Okay? It can give off the electron here can give off the energy. And when it gives off that energy, what happens? It returns to its ground state. So from this time, from n equal to 3 back to n equal 2. In this way, when that process happens, the electron is emitting energy. Okay? Is emitting energy. Giving off energy. This energy is given off in the form of light. So it is actually light energy that we see. There is the energy we're talking about. This, given off by the electron as it moves from the excited state back to the ground state. Okay? That light that we see is the flame color. This is the color of the flame. Color of the flame. Depending on what energy is emitted by this electron, we will see different colors of this light. So the different flame colors exist because elements have unique electron configuration. Now, what do we mean by this? What we mean is that whilst this element here might have that configuration, another element would have a configuration where the distance, for example, between these energy levels, N2 and N3, is not going to be the same as this one. Even that one, it won't be the same as any other element. So when electrons move from there to there in this element, and when electrons move from there to there in this element, the lights, the color of the light, would not be the same. Although they may be moving from energy level 3 to energy level 2 in both cases. So this N3 down to N2. In both cases, they're moving from N3 to N2. But because they are not the same elements, the flames, the colors of the flames are not going to be the same. Okay, so that is why we see different color flames when different materials are burning. All right, and this principle is the same that is applied to LEDs, light emitting diodes, and even with lasers, the same principles. Electrons are allowed to get excited through supply of energy. When they absorb this energy, they get excited and they go to specific, discrete energy levels. And when they are there, if you remove the energy, then the electrons now can lose whatever energy they gained and they go back to their ground state. And depending on the element you are using there or the substance you are using, then you get your colors. You can get your red, you can get your orange, you can get your green in your light emitting diodes in that way. And that is how the principle is applied to actually manufacture or make those diodes. Okay. Now, let's move on. Let's now talk about spectra. And the spectra, we have what we call continuous spectra. We also have what we call emission spectra. And lastly, we also have what we call absorption spectra. Let's go back and look at a continuous spectra. Here, if you remember what we did under electromagnetism, we looked at light and checked the visible spectrum of light, and we realized that under the visible spectrum of light, we have this. We have the Roy G. Beeve. Now, this is something I mastered when I was still doing what we call Standard 5 then. You know, my teacher teaching me general science then told me, look, if we do this spectrum and you want to know these colors offhand, just say it's Roy G. Beeve. And what does that stand for? R is red. We know this is red. This is orange. This is yellow. This is green. This is blue. This is indigo. So let me just write, let me be consistent here. Oh, yellow, green, blue, indigo, violet. So my teacher at Standard 5 taught me that, and I would remember this up to this point. All right, so it's something that was taught properly. Now, let's look at this. If you have got a white light, it breaks up into a spectrum of red, orange, yellow, green, blue, indigo, violet light. This is what we can see. This is what is visible to us. So if I've got this white light here, and I have a diffraction grating here, I am going to have my spectrum there, ranging from red to violet. Okay? Now, if you check here, there is no point where you would say red is ending here or there or there or there. Now I'm starting orange there, and then orange ends here, green there. No. Everything is continuous. In other words, you've got a continuous spectrum. Things move into each other's territory. You just start from pure red or clean, clear red, fading away into orange, then into yellow, then completely you can't see anything that is reddish. You come to green, then green into blue, blue, indigo, and violet. So that is continuous. You don't have clearly demarcated points of these colors elsewhere. That will be your continuous spectrum. But when you look at the emission spectrum, something begins to happen here. You begin to see that the colors are discrete. There is one color, there is another color, some color there is a color there, and there are colors over there. But they are discrete. We know where that color is. It's not blurred with any other color, like in a continuous spectrum. So that will be our emission spectrum. How does it happen? Now, the emission spectrum happens when we have light passing through some element, some substance. Say a hot gas, maybe hydrogen. You allow light to go through here. Some of the light that is in the white, in fact, what happens is that this light goes through this gas here. We know this gas is made up of atoms, and therefore in it we have got electrons, and these electrons are in energy levels, N. Now these electrons, when this light goes in the, remember that light is carrying energy, okay, in the form of photons. Electrons then absorb this energy and goes up, okay, into higher energy state. But as they drop back to lower energy states, to their ground state, they emit energy in the form of light. So one electron will be responsible for that particular light there. Or a range of electrons falling from one specific energy state to the same ground state will give us that light, that color light. Here, another type of electron, in fact, an electron will be falling from a particular energy state to its ground state in that way. So in that way, we have what we call an emission spectrum. Why do we call emission? Why do we call it emission spectrum? Because this spectrum is a result of electrons emitting light as they drop back from excited state to ground state. So they emit that light, and therefore this spectrum is due to the emission of this light by electrons. Hence, we call it emission spectrum. All right. Now, absorption spectrum. Absorption spectrum. Here you could be having, or the same gas, you cool it off. When you cool off that same gas and you allow light to go through, what will happen? Now, when you have cold gas, you are sure that all your electrons are at their ground state. So when you have got this cool gas, you have actually make it cold. You are sure that all these electrons in this gas are at their ground state. They don't have energy enough to get excited because the gas is cold, okay? So because they are at their ground state, if you allow light, white light, to go in here, what is going to happen is that electrons then will start to move from energy levels lower. They are going to start to move from lower energy levels, moving to higher energy levels. And what happens when an electron moves from lower energy level to a higher energy level? What it does is that it absorbs the energy. So when this happens, the electron absorbs the energy. Electron absorbs the energy. Now, where is that energy coming from that the electron is absorbing? It is coming from this light here, the light that has been shown onto this cold gas. Remember, if this is white light, it comes in different frequencies, okay? So some frequencies are going to be absorbed. The absorbed energy will be related to some frequencies of this light. And that means that the energy that has been absorbed is actually the energy of the color that would be extracted or removed from the spectrum. And say this color here, like you see on this drawing, that dark line there says that that color has been taken out, has been absorbed, hence the absorption spectrum. This color has been absorbed by an electron that used that energy to move from a lower energy level to a higher energy level. And because that energy has been absorbed, that light is now not there. So you have got a dark line. You have got a dark line to represent that energy that has been absorbed, that color that has been absorbed by the electron. Remember that the energy absorbed by the electron is associated with a specific frequency, and that specific frequency is associated with a particular color of light. Now, if that energy has been absorbed by the electron, it means in literal terms or in practical terms or in things that we can see, it will mean that that color associated with that frequency has been taken out of the spectrum and it has been absorbed by the electron. So on a screen, we expect to see these dark lines where these colors associated with the frequencies that has been absorbed by the electrons were. So these dark lines here actually mean that the light or the frequency or that energy has been absorbed. Okay? And hence we call this the absorption spectrum. And from the explanation you can see that actually the emission spectrum is actually a reverse of absorption spectrum and vice versa. Absorption spectrum would be the reverse of emission spectrum. All right, let's move on. Let's come to these explanations here in details. Let's look at what is being said here around emission spectrum. Like I was explaining, it's just a consolidation, some summary of what I was saying. Electrons moving from higher to lower energy state. And in that process, they emit energy, and this energy is in the form of light. So we see this light. This is the emission spectra. So we see the light in the form of lines of different colors in that way. Okay? Light is emitted. Now, we also have to know this, that visible emission spectra is possible only when electrons are from any higher energy level but back to energy level 2. Now, that is very important to understand. It does not mean that electrons are not moving from any other higher energy state to any other lower level kind of state, except for level 2. No, that is happening. But what we can see, what is possible for us to see with our naked eyes, is only when electrons move from higher energy states to energy state 2. In other words, that is where the visible spectrum of the energy emitted by electrons is. We can only see it when electrons move from any other higher energy state down to energy state number 2, energy level 2. Okay, and thirdly, we need to also know that the distance between energy levels of atoms, of various elements, are not the same. In other words, for helium, for example, the distance between n equals 1 and n equals 2 is not the same as the distance of n equals 1 and n equals 2 for hydrogen. These distances are not the same because every atom, every element is unique, right? Its electron configuration is unique. So they are not the same. The distances are not the same, and therefore we cannot expect the same behavior of electrons. Hence, we have different colors. The distance is associated with a particular color of wavelength. Now that tells you. It is associated with a particular color of wavelength, with a particular wavelength of a specific color. Okay? So we can see a specific color because that color is associated to a wavelength. And obviously, frequency, because the two are just the inverse of each other. Inverses of each other. Emission spectra provides what we call fingerprints for specific elements. Now, what does this mean? It means that if we look at emission spectra, the emission spectra of a specific element will not be the same to any other one. So we can use that to know that this emission spectra is for nitrogen. This is for helium. This is for hydrogen. This is for sodium. So we can use the emission spectra as we would use fingerprints to catch criminals, okay? But then for elements, we can use their emission spectra and say, this emission spectra is for this one, because we would have studied that and see, okay, for hydrogen, these are the lines we're going to have, and these are the colors that are going to be seen, and therefore this will be for hydrogen. So if we see that spectrum when we experiment with any gas, we will say that this gas that we didn't know was before, we now know it is hydrogen. Okay, so that is used as fingerprints for elements. This will also tell us the elements that certain substances are made of. If we don't know what the sun is made of, we can check at the emission spectra of what comes, of the light coming out from the sun, and check what do we get here? What kind of a gas is there? Then we will be able to tell that, oh, the sun is made up of helium, because it gives us the line spectra or the emission spectra for helium element. Okay, so we say we use the emission spectra as fingerprints for elements. Now, this is just to show that for sodium, for example, this will be its fingerprint. That is the line spectra for sodium. So we see that, we know this substance should be made of sodium. Fingerprints or line emission spectra for mercury, that is the one there. Line emission spectra for lithium, there is the one. So you can see lithium, for example, lithium and sodium are group 1 elements, okay? But look at their emission spectra, it's not the same. So we can't say the same group will give us the same emission spectra. No, no, no. That's why for each emission spectra, we can tell which element it belongs to. So we can tell what a substance is made of, what elements are actually making that particular substance. Right, now, for hydrogen, for example, there it is. What do we have for hydrogen? You can see here we have some red color and some bluish green there, some violet purple colors there. So that is the line spectra for hydrogen. Okay. Now, let's come to the hydrogen spectra specifically. The hydrogen emission spectrum is as follows. You would see here we've got a red color, all right? We've got a red color there, and next to it, we've got some bluish green color. So let's call this one blue-green, okay? Blue-green. This one here, it's moving towards indigo, you can see. So let me call this one indigo. That's not a nice one. Let me see. Okay, takes that one out as well. Blue-green, this will be an indigo color. And right at the end there, you can say this is actually violet. That's actually violet as a color. All right. So that will be the emission spectra for hydrogen. Now we'll be referring to this spectrum for hydrogen a lot as we proceed in this lesson. Some of the examples will actually be based on this one. Let's just proceed and see what comes next. Now we're looking at example 3. Okay, example 3, a hydrogen electron at n equals 1, okay, needs 2.4 joules of energy to move to n equals 3. Determine whether a photon of visible green light, so if we shine a green light to hydrogen with a frequency of 5.56 by 10 to the 14, whether this will be able to provide enough energy to get the electron to move to n equals 3. Now let's write down what is given to us. We are given the amount of energy needed by an electron. So E equals 2.4 by 10 to the power minus 8 joules. And then we are also told that the frequency of the light we're going to use to supply this energy with, which is the frequency of the green light, is going to be, or is 5.56 by 10 to the power 14 hertz. That's frequency, so it should be in hertz. Okay? The question is, find out if the energy will be enough. Okay? This is the energy the electron needs. Okay? Electron needs that energy. This is the frequency. What do we know about the energy carried by a photon of light? We know that the energy carried by a photon of light is given by HF. All right? Now, if it is given by HF, let's see if this frequency of green light is going to give us that energy there. H is Planck's constant, 6.63 by 10 to the power minus 34 joules second, times the frequency of green light, 5.56 by 10 to the power 14. Okay? And what do we get here? We want to try and see if this energy is going to get us there. Let's use our calculator quickly. Okay, so it is 6.63. It is the Planck's constant, 6.63 by 10 to the power minus 34 times 5.56 by 10 to the power 14. What is the answer? The answer is 3.69 by 10 to the power minus 19. So it's 3.69 by 10 to the power minus 19. Okay? Joules of energy. Now let's compare. We need this amount of energy for this electron to move from n equals 1 to n equals 3. Is this going to be possible? 3.69 by 10 to the power minus 19 compared to 2.4 by 10 to the power minus 8. Which one is bigger? Definitely this one is much smaller. This one is less than 2.4 by 10 to the power minus 8 joules. And what does this mean then? Okay, all right? The energy will not be enough for the electron to move from n equal 1 to n equals 3. Okay, means you don't have enough energy to actually do that. So that electron won't be able to do that when a green light is used to get it to absorb some energy. Okay, good. Now let's move on. Let's look at example 4. Right. Blue light of frequency 6.67 by 10 to the power 14 hertz is emitted by an electron. How much energy has been lost by the electron? Okay, so let's answer the first one. The second one says, if the electron moved from n5 to n equal 2, what element does it belong to? Now, this one is not so easy to tell, but we can use that frequency to tell the color of the light, and we can say roughly which element is that. But then we cannot be very, very specific because blue can come in another element, but then but blue combined with others will tell us it's hydrogen, or blue combined with others may also tell us it's helium or whatsoever. Okay, so now we can say here maybe it's going to be hydrogen, but let's then answer the first part of it. The light has a frequency f of 6.67 by 10 to the power 14 hertz. Okay, how much energy is emitted by this electron? Now, this is quite a simple one. You just make use of Planck's equation, E equals hf. That will be equal to, what is h? Is Planck's constant, 6.63 by 10 to the power minus 4 times the frequency given to us, frequency of the blue light, as 6.67 by 10 to the power 14. What will be the answer there? Well, we can use our calculator again, right? Clear that. This is 6.63 by 10 to the power minus 34 times 6.67 by 10 to the power 14. And what is the answer? The answer is 4.42 by 10 to the power 19. So energy is 4.42 by 10 to the power minus 19 joules of energy. That is the energy carried by this photon of a blue light, or let's see, in fact, this is the energy emitted in the form of blue light when the electron drops back to its ground state in this equation. And if this electron moved from there to there, and here specifically, you are told that it is moving to n equals 2, so this emission spectra is visible. Remember that anything down to n equal 2 is visible, but anything down to n equal 1 is not visible, and anything down to n equals 3, 4, 5 is also not visible. What is visible is the emission spectra for electrons moving down to n equals 2. Okay. So here we can just guess that perhaps the color here that belongs to, anyway, we are even being told there, the color is blue, but then to predict what the element is, we can say maybe this is hydrogen, because one of the lines there for hydrogen emission spectra is blue. But like I said, we can't say with certainty here. We have to do other things as well to be sure that this is the fingerprints for hydrogen. Okay, right. Absorption spectra. The absorption spectrum, like I said, electrons absorb energy and therefore take out that color from the spectrum, and therefore you've got dark lines, okay, like that. The dark lines representing where the electrons have absorbed the energy, okay, representing the colors that has been taken out of that particular spectrum. Okay, now absorption spectrum, look at it. If you have got an electron sitting here on energy state 2, and you shine light into this element here, that electron is going to gain energy of particular frequency. Say it moves up to that energy state there. That's its excited state. If this frequency was, say, 5.76 by 10 to the power 14 hertz, this frequency is associated with a particular color. And therefore, that color, by this electron taking the energy of that particular frequency, absorbing it and using it to move from that point to that point, that color has been taken out of the spectrum, and in its place we will see a dark line. We won't see that color anymore on the other side, on the screen. So this is called the absorption spectrum because that energy has been absorbed by the electron and the electron has used it to lift itself from a lower energy state to a higher energy state. So hence we see the dark lines on our spectrum on the screen there. The spectrum now has been devoid of some other colors that belong to it. Some colors have been subtracted or removed from it. Okay. Example 5. Like I said, I think this would have something to do with hydrogen. A beam of white light is allowed to pass through hydrogen gas in a container. A screen is placed on the other end and a spectrum is formed. Refer to the diagram below of the hydrogen emission spectrum to answer the following questions to answer the questions that follow. All right. So here is the first question. Write down the colors that will be seen on the screen. Now, we need to go back to the question and understand it very well. You see here, you've got white light. It goes through a container with hydrogen gas in it. Obviously, at this point, we're not told that this is hot air gas, hydrogen gas, but we're told this is hydrogen gas, and we assume that this is standard conditions. Electrons are at lower energy states. They are going to absorb this energy. If you pass a beam of white light through this container, of course a transparent one containing hydrogen gas, some energy is going to be absorbed by the hydrogen electron, and therefore some colors of the spectrum are not going to be there. Now, the question is, write down the colors that will be seen on the screen. Now, the colors that will be seen on the screen, these are colors that won't be absorbed. Okay? So these are the colors that won't be absorbed by the electron, the hydrogen electron. So it means we need to go back. That's why we need this drawing here. We know that red will go. This is blue-green. And this could still be within blue-green, and this one is your indigo, the second last one. And then you have your violet lastly. So the colors that will be absorbed from the white light are these colors here. But then remember Roy, G, Bev, red, orange, yellow, green, blue, indigo, violet. Now, if this one goes, that goes, that goes, that goes, and this one also goes, what are we left with? Orange and yellow will be the colors that we'll see on the screen. So we'll see orange and yellow. Why? Because these ones cannot be absorbed by the electron in the hydrogen atom. Okay, the electrons in the hydrogen atoms, because remember it's a hydrogen gas, so it's so many molecules of hydrogen inside that container, and then each atom of hydrogen is actually having electrons moving from one energy level to another, and in that way they are absorbing the energies. Okay, so within the visible spectrum, it is only the yellow and the orange that will be seen. The others are going to be absorbed because that will be associated with the frequencies that the electrons will need to absorb to get the energy that will get them excited and move into a higher energy state. The next question says, write down the colors that won't be observed on the screen. Now, obviously, these are the colors that are going to be absorbed. And which ones did we say will be absorbed? We said red will be absorbed. So we won't see red, we won't see blue, we won't see green, we won't see indigo, we won't see violet. Okay? We won't see those ones. Why were the colors in B absorbed? Okay? Why were they absorbed? Because the wavelengths of the colors in B are associated with the wavelength of the electrons as they move from lower energy states to higher energy states. Okay, so that would be the answer. That is how we had to answer these questions. Remember, absorption spectra, certain colors are absorbed because these electrons are taking in energy as they move from lower energy states to higher energy states, okay? And then those colors associated with these frequencies of energy of the electrons as they move are actually taken out of the white color spectra. And then some colors will go, some colors will stay. Okay, you need to be able to know which ones will go, which ones will stay. But then this process is the emission, the absorption and emission spectra, you must know that actually they happen more or less at the same time, because the moment, once you supply energy to an element, electrons move from lower energy states to higher energy states. So energy is being absorbed in that way, or colors are being absorbed of the spectrum. But then if you remove that energy, we expect those electrons to drop back to lower energy states, and therefore emission spectra then happens. So you can first have absorption spectra, then have emission spectra. Absorption spectra, emission spectra. Okay? So perhaps with your light emitting diodes, you will have the flickering lights like that. They absorb energy, they give off energy, absorb energy, give off energy in that way. So you're having all this, both the processes happening at the same time. And then you've got your flickering lights in that way. Okay, now let's come to red shifts. Now, red shifts, we need to start by looking at what happens in absorption spectrum, the absorption spectra from the sun, to understand red shift. Now, when the absorption spectra from the sun is illustrated, what we see is that we've got these dark points here at wavelength in 400. We've got that between wavelength, at wavelength 500, between it we've got that and that. We've got this one at 600, that dark line just before 700. So that's what we have. Now, if we look at an absorption spectra from a distant star, for example, and we see the same thing with some kind of a pattern here, we see that this dark light has now, if you check here, it has moved from there, from 400, it is now at 500 at this point here. It is the same one, this dark one is there now. This one is this one. That one is that one there. This one is this one here. And that one is that one there. These ones have gone beyond, okay? Gone beyond what is visible here. They've gone into an invisible region. Invisible region, because that's invisible region, and also down this side will be an invisible region. Now what has happened? This one is shifted to that point. In fact, this one shifted to there. This one shifted to that point. This one shifted there. And these ones are not visible anymore. Now, what has happened now? You would see that there has been this absorption spectra has actually shifted from the blue side to the red side. Shifted from the blue, let me just give you space here, blue to red. Okay? And because the shift has been from blue to red, we call it a red shift. A red shift. Now, because this was some star giving us this shift here, remember, the absorption spectra from the sun is that of helium. So it tells us that the sun is made up of helium gas. It is made up of helium gas. Okay? Now, if we still find this spectrum of the helium gas for a distant star, we're still finding the same pattern, the same absorption spectra. What we can say is that this star is made up of helium because this is the fingerprints of helium gas. But what we can also say about this star is that it would tell us that this star is actually moving away from the Earth, from where we are. Moving away from Earth. Why? Because we're moving further into lower wavelength, into lower frequencies and higher wavelengths. So this region of the red here, we have got lower frequency. Okay? Lower frequency, so we're moving towards the lower frequency region, and therefore this means that this star is actually moving away from the Earth, moving away from the people observing it from the position of the Earth. Okay? Now this part here was only done to help you see how the shift occurred. So something that was at 400 now is at 500. Just after 400, it's above 500 over there. Here, something that was just just before 500 is after 500. After that, okay. So this is just something to illustrate the shifts there. Okay. Now, if we then look at this diagrams here and showing the red shift and everything, we're saying this star, the distant star, seemed like it's moving away from the Earth, and it is there. Why? Because we're seeing it moving into the region of lower frequencies. If something is, if the frequency of something seem to be becoming smaller, decreasing over time, if we're talking about sound, for example, what comes to your mind? Doppler. So this actually can be explained using the principles under Doppler, because we're talking about a shift from higher frequencies, the blue side, the violet side, the blue side, down to lower frequencies of the red. So we're talking about a change in frequency, an apparent change in frequency, something that is observed as a change in frequency, and therefore that has something to do with Doppler. All right. Now let's look at this example here, example 6. The 432 nanometer line on the hydrogen absorption spectrum appears at 610 nanometer region on a spectrum collected from a distant galaxy. Explain how the galaxy is moving relative to the Earth. Okay? Relative to the Earth. Now, firstly here, we need to know that this galaxy is moving from a point where it was 432 nanometers. Now, this is wavelength. To where it appears to have a wavelength of 610 nanometers. Now, the first question we need to ask ourselves is, have we seen what is happening to this wavelength here, to this lambda? Is lambda increasing or decreasing? And what we see is that lambda, the wavelength, is actually increasing. It moved from 432 to 610. Now, if lambda is increasing, if wavelength is increasing, what is happening to frequency? Frequency is decreasing, is becoming less. Now, if frequency is becoming less, what is happening to this galaxy relative to the Earth in terms of its motion? Is it moving away from the Earth or moving towards the Earth? Definitely, it is moving away from the Earth. Doppler tells us that if frequency decreases, it means that the source of the energy, the sound is moving away, or the observer is moving away. Okay, so, or both are moving away from each other. So what it tells us here, it means that the galaxy is moving away from the Earth. This one is moving away from the Earth. So what kind of shift do we think is happening here? It is actually a red shift. Okay? The absorption spectra is moving from the high frequency area into low frequency area. So it's a red shift. We call it a red shift, shifting towards the red end of our spectrum. Okay? The last part of our lesson, scattering. Okay? Now here I've got a picture. This is the picture of the moon. So here you've got the moon here. And the Earth. You've got the Earth there. If you are standing here on the moon, okay, you are there, and watching the Earth at a distance, it looks like the Earth is rising, okay, rising. The Earth is actually rising. You won't say the moon is rising. You will be saying the Earth is rising. Now, that's the beauty of relativity. You are on the moon, you say the Earth is rising. But if you were on Earth, you would be saying the moon is rising, okay? Good. Or the moon is actually going down. Now, the Earth is rising. You are on the moon. You're seeing the Earth rising. But here, all you see, it's dark. It's a dark atmosphere, right? This part here is dark. Why is the atmosphere appearing dark here, but when you're on Earth, it appears blue? And that is the issue that we want to try and explain here. Now, scattering happens when light passes or falls on gases in the atmosphere. Okay? And when that happens, is that if this is a gas molecule and this represents light from the sun, it hits the spectrum, from the spectrum of white light, the light with lower frequencies is absorbed, and some of it is allowed to pass through, so it's transmitted through the gases. But light with higher frequencies, okay, so that is one point happening. The second thing is that light with higher frequencies is reflected in all directions. Light with high frequencies is reflected in all directions. Now, what is this light with those high frequencies? We're talking the violet blue area. So blue is what we see easily compared to violet. So this blue color, this blue light is the one that is reflected. Now, if, again, let me use a different color here. If this represent gas molecules, and this black one represent white light or light from the sun, it hits there, part of it absorbed, the red, the green, okay, the orange, the yellow absorbed there, some allowed to pass through. The blue reflected in all directions. If it is reflected in all directions, we can say it is being scattered. Hence, scattering is what we're talking about here, scattering of the white light. Now, these ones that are reflected in all directions are mainly blue color light, the blue color frequency. Now, the sky then appears blue. The sky appears blue. But then the question is not saying why is the sky appearing blue? The question now is, why is this appearing black, this atmosphere from the moon appearing black? Why? It is appearing black the atmosphere of the moon appears black because it has no gases. There are no gases there. We're talking about a vacuum. Okay? It is the gases that are responsible for scattering the white light to give us the blue color in our atmosphere from the Earth. But from the moon, we don't have those gases, and therefore, in the absence of those gases, there is no scattering happening, and therefore, the sky there appears black. Well, that brings us to the end of the lesson today. I hope you enjoyed it. And from me, Tinyiko Kosa, it's goodbye.